Hey everyone, welcome to Science in Perspective. So in this episode, I'm going to jump into some pure mathematics, some recent research that's come out of pure mathematics that I think has a strong bridge to really all of science and really life writ large because of the way it speaks to an ability of a formal system to access truth. So I'll give you a little bit of background on what I mean by that. It relates to mathematicians like Cantor and Gödel who showed that formal systems like mathematics have a limit to them. There's an incompleteness. You can't prove everything with them. And Turing did this on the computational side of things. You can't program everything. There's always a computer program that's out of your reach. So there's this unreachability to things like mathematics where they just can't prove all things. And I'm going to kind of have a minor argument in this episode where I say, well, the stuff that it can't reach is most of everything. Like if you really think of what matters, if you really think about the way humans pick up on truth with our consciousness, right? Pattern recognition, intuition, the leaps of intuition that we use really that undergirds all type of discoveries. You know, it's that really accesses the truth that we need, and then the formalization just comes later. So the stuff that math isn't getting, provably isn't getting, isn't reaching, the stuff that computer programming isn't able to program, is the overwhelming majority of truth that arguably exists in nature. So I'm going to kind of make that minor argument, but then more to the point, I'll make my main argument that says that is not necessarily the end for mathematics or other formal systems. I think there is a way for these formal axiomatic systems to access truth if we change the way we use them. It has to do with mathematics and computer programming being embodying a more kind of creative version of what they do. I don't mean the people doing them being creative. I'm not saying mathematicians need to be creative and computer programmers need to be creative. They already are in many ways. I mean the math itself has to create and the computer programming itself has to create. So I'll give you some background and talk about what that means. The research that I'm talking about, it's Juan Aguilera. He came out with a paper in 2024 and this is, it's called Large Cardinal Structural Reflection and the HOD Conjecture, the HOD Conjecture. You know, we don't need to get into a bunch of details, but it has to do with basically Cantor's hierarchy of infinities. So if you don't know already, infinities can be different sizes. Okay, if you take the infinities, or if you take, let's say, the whole numbers or the natural numbers, which are the numbers that we count with, 1, 2, 3, 4, 5, and you go forever, that's one type of infinity. But you could also take the real numbers, which are the decimal numbers, 1.12, 1.2, whatever, and you can take an infinite number of those. Well, the infinite of real numbers is actually provably larger than the infinity of the natural numbers. Okay. And so you would say, like, you know, the natural numbers are countably infinite and the real numbers are uncountably infinite. So anyway, it turns out there is a whole hierarchy, potentially an infinite hierarchy of infinities. In other words, you can keep getting bigger and bigger and bigger infinities. And this is what Cantor did back in the day originally. He used, what we call a diagonalization argument, and he showed that no matter how big of a set or a collection that you grab, you can always create something in that set that wasn't in there originally. It doesn't matter how big it is. In other words, you could even grab like an infinite set of something, and within that infinite set, which you would think is everything because it's infinite, you can create something within that infinite set that wasn't in the set originally. So it kind of goes beyond itself. So it's this kind of contradictory, weird result that you get with mathematics. And you can go look up the diagonalization argument. It's a little hard to describe it without a whiteboard, so you can see how it works. But basically, you're taking, it's called diagonalization argument because if you lay out, let's say, all the combinations you could make from a set, and then you change, let's say, what you're grabbing from that set are all the decimal numbers. So you take the real numbers, and you take a collection of that or an infinite amount of that and you lay out all the possible decimal numbers you could have, and you take the nth digit of the nth number, so the first digit of the first number, the second digit of the second number, the third digit of the third number, it makes a diagonal, and you change that number along the diagonal, then you end up creating this new number that was never in the original set. So you can go look that up and get some background if that sounds a little bit weird and you're not exposed to that already. The take-home message for the sake of this episode is the fact that you are able to, in a contradictory fashion, create something beyond what the formal system was able to capture itself. And you're creating it with the formal system. So in other words, you can take mathematics and you're able to create something with mathematics that mathematics itself can't prove. Okay? And there's a programming version of that too in computer science, where Turing would do this with computer programs. So anyway, so Cantor has this proof, this diagonalization argument that shows kind of the first hint that there's something funny about mathematics, that it doesn't seem to be able to reach the full truth because it can almost contradict itself, right? It's not able to fully reach or capture or model, if you will, its own internal systems or anything that it wants to model out there in nature, because it's got this limit to it. It can't even prove itself. It's just this contradictory kind of result. So that's Cantor. And then Gödel comes along and does basically the same thing but just with mathematics. So Cantor was kind of was doing it with countable systems, still a part of math, but countable systems. Gödel comes along and basically does this with all mathematics. He says, I can associate any mathematical formula with a number, and then those numbers can be like countable or uncountably infinite, right? Countably or uncountably infinite, similar to what Cantor was doing. And I can show that mathematics itself ends up in that same situation where you can take anything from mathematics, you can kind of create something new with the mathematics, which the mathematics itself can't capture. Again, super counterintuitive, super contradictory, right? Like you're using math to make something that math can't do, but you used math to make it. Sounds very counterintuitive, but it's really at the heart of some of these major proofs that have come out in mathematics. And then you have Turing, which comes along and does basically the same thing again. He used what is essentially akin to a diagonalization argument to do it with computer programs. And he says you can use computer programs to essentially make a program that can't be computed. Again, if it doesn't make sense, it's kind of not supposed to, because it sounds like I just contradicted myself, right? Which I did. But that's the point, is you can make something with the computer programs that the computer programs that themselves can't compute, is one way of saying it anyway. So we can say that, Cantor came along and said you can create a new number by changing the nth digit of the nth number, and it proves that the real numbers are uncountable, and it actually means it's a bigger infinity than other infinities, okay? Gödel comes along and says, he makes a word version of kind of a mathematical statement or formula, you might say. It'd be something like, this statement cannot be proven in this system, right? And so if it's true that this statement cannot be proven, that can never be proven, and if it's not true, then the statement's false. It just contradicts itself, right? Like it doesn't seem to make sense. And yet we can perceive the truth of that statement. It doesn't, from an axiomatic system, like if you're trying to be very precise about the definition of truth, you would say that statement doesn't make sense. This statement cannot be proven in the system. Well, it makes sense, but there'd be no way to kind of reconcile that with the perfect system, right? Because it seems to contradict. But that's just the incompleteness of formal systems that Gödel was showing. And then Turing says, if you were to make that as a statement, you might say he's saying something like, this program halts if and only if it doesn't halt. And it proves the halting problem is undecidable. And so, at a high level, it doesn't matter whether you're talking about Cantor or Gödel or Turing, right? Whether you're talking about counting systems or all of mathematics or all of computer science, let's say, at least in terms of the rules-based Turing machine type computation that we think of, that we usually associate with computers. Doesn't matter what system you're looking at. These very formal systems that we use that try to be very precise, right? Computer programs try to be very precise. They're all explicit rules. Mathematics attempts to be very, very precise about the way it defines things, right? Counting systems is very precise about the way it does enumeration. When you try to be that precise, you'll never be able to access full truth. And you can show that in kind of a meta-mathematical way, right? You can show that, you can prove that it just cannot access truth. Okay, so I hope that made sense. And again, go back to Cantor if you kind of want that example. If Turing and Gödel are a little bit hard to understand, just go back to Cantor, look it up, and see what he did with the diagonalization argument. Basically, you take a formal system, you create something with the formal system that was never there. And you can always do that. You can always go beyond what the formal system can capture. So it's that going beyond the incompleteness. It's that undecidability that's really interesting. And just says these formal systems can't reach all truth. Okay, so and part of that ties back into, I said there's this research paper that came out about large cardinals. So the thing that you can keep kind of creating that wasn't in the system before is these new cardinals, is these new infinities, right? That's a kind of an example of that. And you can just keep creating. You basically take the power set of a set. So a set is just a collection. I take a collection. If a power set is kind of think of it like a sample from that set. It's almost like loosely analogous to like what you would do in statistics. If there was a big population and I had to take a sample from the population, right, to know what the population thought, kind of, right? So you take a collection and then you take a power set from that, which is like a sample from that. It doesn't matter how big it is. And you can take a power set of the thing you just took a power set of, and you can keep taking power sets and you can keep building bigger and bigger infinities. Well, eventually these infinities get so monstrous and so huge that some people in set theory and pure mathematics just want to study them. And they kind of study them almost like it was a science, because now you're basically just trying to research the universe of mathematics. Like, how crazy do these infinities get? For the most part, the infinities behave the way you would expect. They kind of behave nice and linearly, right? Like they get bigger and bigger, but they kind of get bigger in a predictable fashion. They don't start behaving wildly. But if you get really big and really monstrous, all of a sudden some infinities start acting kind of chaotically, and they interact with let's say the infinities that are lower in the hierarchy in kind of an explosive fashion. They just don't follow the usual pattern of infinities that you would expect. So something's happening. Juan Aguilera and others, as they do this research at these large cardinals, they're looking at what they call exacting cardinals and ultra exacting cardinals, basically just really big infinities that, again, you can keep creating, just keep taking the power set, keep creating something that wasn't in the system before it. And you create these monstrous things, right? It's still within the system of mathematics, but it's not enumerable by the set that was before it, okay? Another way of thinking about this, without getting into too much detail, is it's like there's no bijection that exists between the set and its power set. If you were to take one set of things you collected, like the natural numbers, right? And then you take the real numbers, you can't draw a line between all the natural numbers and the real numbers, because there's always more real numbers. And if I take another power set, it's the same thing. I can't use the reals to count the power set of the reals. And now I can't, and you just keep going, you keep creating these bigger things. Okay, but what I want to touch on is what these researchers are running into, which is really interesting, because they're looking at the universe of mathematics, and they use techniques like reflection and embedding. You can kind of think of reflection as homing in on a smaller part of the mathematical universe, let's say of this hierarchy of infinities, and trying to understand its local behavior and see if things are kind of logically consistent between areas. You can kind of think of embedding as kind of almost like a structure preserving map between areas of the hierarchies, right? The universe of mathematics. That's kind of like, if you have any exposure to category theory or something like that in mathematics, then they try to, basically a structure preserving map says, I'm going to change a bunch of stuff, but I want something to not change as I go from here to here. And if a bunch of stuff is changing, but this isn't changing, I learned something about the thing that was preserved. That's one way to think about structure preserving maps. Anyways, so reflection, embedding, they do these mathematical tricks and they learn about these infinities. And that's how they're starting to learn that as they get really, really big, like these exacting and ultra exacting infinities, they just start to get very explosive and act chaotically and don't follow the quote unquote rules that were being obeyed by the other infinities in Cantor's hierarchy, if that makes sense. Okay. So why is that happening? Why are things just exploding out of nowhere? And what does that have to do with the reachability of truth, right? Well, okay. So first I'm going to make that kind of minor argument that it can be a major argument in a different discussion, but for the sake of this episode, I want to make this first argument here that, the stuff that math isn't reaching, like when you can use math or computer programming or any axiomatic formal system, right? Some very precise system, when you can create things with it that the system itself couldn't capture, it's almost like it can create things that it can't reach. It can create things that it can't count, right? The system can create things that it can't program, right? Again, there's that contradiction, right? When you do things like that, I think a lot of people think that, well, whatever math, let's say, is not reaching is like an edge case, right? Because math is everywhere. It's used in science all the time. Hey, it's doing a great job, isn't it? So even if, Kurt Gödel was right, which provably he is, that there's this incompleteness to mathematics, isn't that just kind of like maybe some edge case stuff? Well, no, I think it's the overwhelming amount of truth, probably. And the argument there is you have to just think of how we evolved as humans, right? The most complex phenomenon that we know of is the human brain, and it's able to access what we call truth on a regular basis, and it's been able to survive from an evolutionary standpoint over millions of years, and it doesn't do things mathematically, like at all, right? It's like nothing like math. It does things with heuristics, it does things with high-level abstractions, it does things with pattern recognition. Sometimes we call it gut feeling, sometimes we call it intuition. And that type of thinking is at the heart of everything. You might call the system 1 versus system 2, right? Where system 1 is more natural, quick, heuristic, and then maybe the system 2 is more logical and analytical. Well, the latter is kind of just an artifact of modern society, right? System 2 doesn't really exist. It exists. I shouldn't say it doesn't exist, but it's not like we didn't evolve for the most part to have that type of thinking. There's a time and place for it. But that's kind of a byproduct of our modern gamified world where we put everything on a grid and now we think that we need to calculate things very specifically. The natural way the human mind is working is through high-level abstractions, broad pattern recognition, and intuition, which is not a hand-wavy, fluffy thing. I mean, obviously, intuition is part of the arsenal of the human mind when it comes to problem solving. And let's be clear, the human mind is solving harder problems from a computational standpoint than anything a computer is doing, although AI is obviously catching up. But that doesn't go against what I'm saying because AI is taking on the type of thinking that humans do anyway. Right. I'm not saying it's at parity, but it's obviously extremely analogous, if not the same thing. It's becoming a complex phenomenon, right? So when it comes to truth, right, like you wouldn't be able to do any type of mathematics or any computer programming if you didn't make intuitive leaps. There's no way because people have to look at a system and they have to have an intuition about something and say, I think there's something worth working on here, right? I think I can prove something mathematically. I think I can create a piece of software that does this. I think Turing had to come up with the Turing machine as a model. Gödel had to come up with it. All mathematicians, Juan Aguilera, everybody doing this, whatever it is, math, cooking in the kitchen, it doesn't matter what it is. You have a feeling about something, right? We don't like to think of feelings as related necessarily to problem solving, but of course they are. They evolved over millions of years of hominid evolution. So yeah, they're real. And they're an anchor to kind of the heuristic pattern recognition that we use to solve truly hard problems. So truth begins with intuition. Truth begins with those leaps that we make with our consciousness. And it's not really that hard to argue that whatever our consciousness is doing when it makes those decisions is probably beyond what any formal system can capture, right? We already know there's an incompleteness to formal systems. We already know that formal systems, like symbolic reasoning, doesn't look anything like what our minds are doing. We don't... I'm pretty sure most of us aren't shuffling symbols in our mind as we solve problems in the real world. If you're trying to find your way out of a forest, you're not analyzing the situation in that symbolic way, right? So we already know that, right? And so what impresses upon you as a human being, those leaps of intuition, the true truths of things, is something like that intuition, that pattern recognition, that high-level stuff. And we already know formal systems can't access it. So again, why I'm saying this is when we talk about the incompleteness of axiomatic systems, it's really, really incomplete. Like, I don't think it's like only the edge case. I think math isn't even remotely close to getting to the truth, okay? And you can argue this further because if you take a look at artificial intelligence today, which is arguably passing the Turing test, I mean, everything but passing the Turing test, right? I mean, you could have a 5-minute conversation if that's what you want to use as your benchmark for genuine intelligence. Nobody would know that was a machine anymore. These large language models, and now again, they have a lot of improvement. They can still make some stupid mistakes, but for the most part, we've achieved AI. Maybe not AGI fully, but we've achieved AI. I don't think that's really debatable, at least in the natural language processing space, which is most of everything anyway. Okay, so if you look at these AI systems, well, they're not using rules-based programming to achieve what they achieve, right? There's rules-based programming in there from a scaffolding perspective, but then you let these systems go. And they become genuine complex entities that are using billions and billions of parameters to produce outputs that no scientist or engineer alive knows how it works. We don't, right? You can peel back the layers. There's no causal deterministic mechanism from input to output because it's not software as usual. Artificial intelligence today, right? The connectionist approach, right? Symbolic approaches to AI have all but failed, right? Those might have little cursory roles that get layered on top of connectionism, but connectionism by far is the only approach that we know of that works because it allows the system to emerge itself. In other words, you cannot program the rules into AI. If you wanted to make a facial recognition algorithm or system, you would never do that with rules-based programming. It would never work. It never has. It never will. Right? I mean, this gets right into the P versus NP problem, but that's beyond the scope. There's no way this is going to happen, right? Because there's not only will you never be able to collect enough rules, there's no reason to believe that the pattern recognition underlying facial recognition runs off rules. It's not some simplistic additive collection of rules that comes together to lead to facial recognition. It doesn't make any sense. It would have to be something multiplicative. It would have to be a multiplicative process, a nonlinear process, something that gets embodied in genuine complexity, right? Complexity is not just a word you throw around. It's got a very well-defined definition, actually. It's many pieces that interact to a great degree. And because of that, it takes on properties in the collection that are not there in the fundamental pieces that went into the collection, okay? So complexity is a very different thing. It's not more, it's different, right? So the human brain is not more, just more connections, right? It's completely different. It embodies emergent patterns. And emergence, in many ways, is the antithesis of axiomatic systems, right? The emergence doesn't look like, even if you put math into AI. In fact, let's use that as an example. So if you said, well, is mathematics used in artificial intelligence? Well, yes. Is it thanks to mathematics that AI produces its outputs? Well, no, not directly, right? So you're going to put mathematics, for better or worse, we're going to use mathematics to basically mix and match the data within AI systems, okay? So we're going to come up with some cross-entropy formula within the objective function, right, between what's predicted and what actually is in order to run an optimization problem and close the gap, blah, blah, blah. Okay, if you know anything about AI, right? So you can set all that up mathematically, but that's not how the outputs are produced, right? The outputs are produced because there's millions and millions and millions, if not billions of iterations and an absolute ton of variation from an absolute ton of data and backpropagation and selection and levels of abstraction that emerge that were never programmed in there and that quite frankly have nothing to do with mathematics, right? It was set up mathematically, but then the system runs on its own. And the truth, this brings it back to what I'm talking about, the truth that AI embodies, which of course it does to a large extent, because otherwise you wouldn't be having conversations with large language models. It wouldn't make any sense. The truth that it embodies is emerging. It doesn't come from a formal system. So mathematics is used to set up AI, but mathematics does not produce the outputs in AI. Rules-based programming is used to set up the scaffolding of AI, like the data pipeline and even setting, let's say, hyperparameter values, and everything, the neurons and all that. But that alone is useless. Once the data goes through and does millions of iterations, that has nothing to do with rules-based programming, right? The outputs, if it did, you would be able to trace back where the outputs of AI came from, and you can't and will never be able to do that because that's not how emergence happens. Okay, it's not even up for debate. Emergence is the absolute antithesis of symbolic reasoning. It's the absolute opposite. It's diametrically opposed to the notion of rules-based programming. Okay, so there's a big difference in AI between setting something up and the truth that AI systems are able to embody or access. Okay, same with the human mind, right? At some low level, maybe there's something kind of mathematically happening or something akin to that. But when it comes to me being able to speak like this and do pattern recognition and have this kind of dexterity, that's nothing to do with symbolic reasoning or rules-based programming. It's an emergent phenomenon, right? So we know that it's genuine complexity and emergence that accesses genuine truth. Because again, going back to what I said before, it's intuition that accesses the truth. Once you have the intuition and you go after something, and your intuition can still be off, but there's still always intuition there. Because even if your initial intuition was wrong, and then you try to formalize something with mathematics, and then you have another leap of intuition that corrects it, it's still the leap of intuition. You can't, there's no way to look at a mathematical statement and know that it's correct without intuition. Right? Because you have to operate at a level that's meta to the mathematics itself. You have to be able to comment on mathematics. You can't validate something unless you're standing from the outside and commenting on it. It has to be meta. That's what meta is, right? You have to have self-reference, right? So you can't validate a mathematical proof without intuition, actually. No matter how internally consistent the language is, the only way you can look at that as a human or an AI is in a self-referencing fashion is to step outside the world of mathematics and to validate that this is mathematically correct. The math itself, right? So that's that unreachability. That's that undecidability. The mind is able to go there. And because that's where that is the ultimate truth, right? Because if you can't validate mathematics without going meta to the mathematics, right, without stepping outside and having intuition, then you wouldn't have any truth anyways. There'd be no such thing as mathematical proof. You can't just use the system itself. You have to be able to observe the system from the outside. Okay. So anyways, so now we go back to Aguilera's research on these large cardinals. So why are they exploding? Why are they acting all crazy? Well, maybe that's mathematics itself reaching a type of genuine complexity. Because one thing you can say about Cantor's hierarchy of infinities, which is what these guys are essentially dealing with, just creating huge ones, is as the infinities get larger, they don't just get bigger, right? Cardinal means size of the set, basically. Those sets don't just get bigger and bigger. They get more internal complexity to them, right? Arguably complexity. They get more internal intricacy, configuration. There's more configurational dynamics. Remember in the last episode, right? I was talking about entropy, different microstates mapping to macrostates. The internal configuration space is starting to explode and get more and more, and you should expect there to be interactions between the pieces within the larger and larger infinities. So arguably, by any definition of complexity, those higher infinities should be starting to basically exist at the edge of chaos or beyond chaos, because chaos is still deterministic, to go beyond chaos into genuine complexity. And maybe that's why they're getting it. Now, I don't know, but this is my opinion. Maybe this is why they're starting to act unwieldy and they're starting to explode. They act explosively with the other parts of it. It's a wild, wild west out there now in the universe of mathematics. Now, why that might be interesting and good is because, again, if you're just talking about Cantor, Gödel, and Turing, you can kind of throw up your hands and say, well, mathematics isn't going to be able to reach all truth. And that is what you should be saying if you're just looking at those scientists, or mathematicians, logicians, and computer scientists. That is what you should say, because that is what they showed. And also, if you look at AI systems and or the human brain, I don't think math is even remotely close to the truth. Right? Those formal axiomatic systems are not even touching anything that even looks like intuition and pattern recognition, which, of course, for the arguments or for the reasons I've made, is ultimately where all the truth is coming from. Because you got to be meta, you got to observe from the outside. You have to have a leap of intuition. So you've already got that incompleteness, and that everything beyond the incompleteness is the majority of truth. But so you might say at that point, okay, so we're doomed. Math can't even do that much. Actually, we think it can because we use it all the time, but maybe it can't do that much. But if math is unleashed in a creative fashion, the way it is in AI, remember I was talking about these AI systems. The humans will set up the mathematics in the AI, but then it is let go. It is let loose through millions, billions of iterations. It does something in ways we don't know. It creates within itself because of that interaction. Inside AI systems is an absolute a massive amount of interaction, an absolute ton of configurational explosive space there that is interacting with itself. Genuine complexity, genuine emergence. So maybe math can achieve that type of emergence if it's let loose like that, which means math has to be used creatively. Again, I don't mean the mathematician or the human being creative. I mean math has to be let loose. And so one way to let it loose is within systems like AI, is it within machines, because humans can't let math loose. They can be creative themselves, they can be intuitive, and then they can do precise symbolic reasoning with it. But they can't let it loose the way an AI system does, mushing mathematics together with billions and billions of iterations so that genuine emergence can happen. Going to explosive infinities where math starts to take on genuine complexity, meaning maybe formal systems like mathematics can reach the truth, can go beyond the incompleteness if they're allowed to themselves create. If computer programming as a formal system can get creative, that you're not going to get that with rules-based programming unless you unleash the rules-based programming in an optimization problem and allow it to go through billions of iterations. Now it's no longer about rules. Now the mapping from input to input is happening by emergent levels of abstraction that come from a massive level of interaction. So it's a way to get rules to not act like rules. I'll say that again. It's a way to get rules to not act like rules. There's a way to get math to not act like math. If you put it in systems where it can unleash a creativity, and it is a creativity because you're getting emergence. What else is creativity, right? It's a massive amount of trial and error, and something emerges out of that trial and error in a non-deterministic fashion. That's what happens in AI. That's obviously what happens in the human brain. Okay, so we have to use formal systems differently if formal systems are going to be able to access the truth. Okay, pretty much everything that is all of, whether you're talking about computer programming, whether you're talking about mathematics, whether you're talking, probability, all this stuff, it's all based on enumeration, which is why it all fails. It all goes back to Cantor, right? Cantor showed with enumeration just means counting, right? If you try to count stuff and you try to you try to use this system to count another system, and that other system is of a particular type, you'll never be able to count everything in that other system, which makes, even if this is infinite, you'll still never be able to count the system over here, right? That's like the natural numbers versus the reals. But it doesn't have to be numbers. You can do this with computer programs. You can do this with anything. Blocks of wood, maybe. It doesn't matter, right? If you're counting, it's the counting that's the problem. It's the counting which is at the heart of all formal systems. All computer programming, all mathematics, all axiomatic formal systems rest on enumeration. That's the problem. It's not always a problem. Sometimes it's a superpower, right? Because counting can do a lot of things. But it is the fundamental problem. It is it is enumeration that sets the boundary to completeness, which is why mathematics will never be, as an enumerative system, it'll never be complete, right? But if you unleash it in a creative way, the way an AI system would, the way the human mind would, right? Then you're no longer just counting. You're no longer basing things on enumeration, which gets you past the limits of Cantor, which gets you, arguably, I would argue, I am arguing in this episode, gets you past the limitations of Gödel, which gets you past the limitations of Turing, and anybody else that wants to use a diagonalization type argument to systematically show that you can take any formal system but create things that are not in the formal system. Now, there's one other way to do this too. You don't just have to unleash it in like big systems like AI, because what if you just want to do this as a human? Like, how would you use mathematics like that? Well, the other way is to stop, is to make sure that you only do mathematics to characterize things post-emergence. Okay, so in other words, don't try to use mathematics to explain causally how something came to be. Okay, that's just a ton of narrative fallacy. It's a ton of fiction. You know, if the phenomenon you're looking at is complex, which is going to be almost everything unless it's in the vacuum of space, right? That's why so much physics was done by looking at space, because, you know, there was no complexity there. As soon as you come back to Earth and there's a complexity, three-body problem and beyond, just falls apart. Okay, I get it. You can use approximations. You can still do lots of mathematics on Earth, but the limitations are severe. The approximations are gross. But if you do everything post-emergence, okay, so you let biology or whatever do its thing, the pattern comes out, and then you just characterize that pattern. You're not trying to causally explain how it came to be. You're not pretending there's determinism where there's not determinism. You're just characterizing it, which is a great use of pure mathematics, by the way, right? Just characterizing the properties of something. Then that's another great way to use it, because now you're not, because now the complexity has already happened, okay? So in other words, the math itself has to take on complexity like it would in an AI system, or you have to let nature do the complexity and then just characterize the complexity. Don't causally explain it, just characterize it. It has this property, it has this property. It fits this symmetry. I'm going to use group theory to show that it does this. I'll use category theory at a meta level to show it does this. That's all great stuff. But don't try to pretend like you causally know how something happens, right? Here's my Ising model to explain how complexity happens. No. Don't try to causally explain how something happened. Just characterize the properties of it. I hope that makes sense, because the emergence has already happened, right? Okay, anyways, that's it for this episode of Science in Perspective. So again, there was some pure mathematics research that was done. I thought it was really interesting. They were exploring these infinities, and the infinities start to explode. And as a scientist, you can kind of look at that and say, that sounds kind of familiar. Things existing on the edge of chaos, things taking on massive configurational spaces. Hey, we know all about that stuff. You know, that sounds like complexity, right? But you don't think of mathematics reaching complexity, because you think of it as kind of analysis and symbolic shuffling. But anyways, if you look at systems like AI, if you look at the way the human brain works, if you look at emergence, if you look at complexity, and you think, well, maybe that's what mathematics is reaching, it means even formal systems like math or computer programming, countable systems, maybe they could reach the actual truth the way our intuitive minds do, if they're unleashed in that creative way. Anyway, I hope all that made sense. So that's it for this core episode. And premium members get to listen to the extended version while I keep talking some more about this kind of stuff, get more into some of the details. But anyways, that is the core episode. So thanks so much for listening. If you want to become a member, go ahead and check out scienceinperspective.com, science-in-perspective.com. And free, regular, most of it's free. You get access to content, visual summaries, all that kind of stuff. But premium members get the extended conversation for each episode, and also premium content related to mindsets and techniques for learning science. Okay, thanks so much for listening. Until next time, take care.